Okay, and now on to the ambiguity function. The matched filter, let's quickly review matched filters. A matched filter is a cross-correlation between the received signal plus noise and a replica of the transmitted signal. Here's the transmitted signal, the round-trip time, and here's the matched filter output. For low signal-to-noise ratio, and you have to assume low signal-to-noise ratio or you wouldn't see the target, the autocorrelation of the transmitted signal is that, and it's assumed that the Doppler velocity of the target is 0. Usually the target's moving and the Doppler frequency of the target is not 0. Then the output of the matched filter is the cross-correlation of the transmitted signal and the received Doppler shifted echo. The ambiguity function is the squared magnitude of that cross-correlation, the output of the matched filter, of the transmitted signal and the received Doppler shifted echo. Studying this two-dimensional plot of the ambiguity function as a function of Doppler and the delay time range of the target, studying it analytically and graphically in 2 dimensions is what we're going to do, as a function of the time delay, which is range, and the Doppler frequency, which is the Doppler velocity. It gives us great insight into understanding many of the waveform's property, in particular the target resolution with a given waveform, the waveform measurement accuracy, the response to various types of clutter, and the ambiguities that you're going to have in range Doppler space. Okay, now we've said this before, and thus with some algebraic manipulation, and on these 2 pages of Skolnick the 3rd edition of his Introduction to Radar Systems book, this is the ambiguity function without its amplitude squared. So thus the ambiguity function is the absolute value of this quantity squared, where capital T sub r is the round-trip delay time, the echo time, proportional to the range of to the target, and F sub d is the Doppler shift of the target, with the signal being this. Okay. Now here are some of the properties of the ambiguity function. The maximum is twice the energy quantity squared, when the true location of the target is at 0 range, when the Doppler is 0. And the total volume under the surface of the ambiguity function is twice E2 quantity squared. And the behavior along the x-axis is the autocorrelation function of u of t, and the behavior along the frequency axis is the square of the inverse Fourier transform of u squared of t, where u of t is this amplitude. A good model for the ambiguity is suggested by Merrill Skolnick, and he says it's a box of sand. And the total volume of the sand is twice the energy in the pulse squared. And the sand can be in different piles, but its volume is constrained to be 2e squared. So you'd effectively have a delta function if the target was at 0. And that's an unphysical property. Now, there are 3 general classes of ambiguity functions. And note I'm plotting here just the magnitude, not the magnitude squared of the ambiguity function. A knife edge or ridge form, what we call a thumbtack form, where we have a slab of energy and a well-defined spike. Here we have a ridge that's pretty sharp, and it can be at an angle to the Doppler axis and the range axis. In the case of a frequency modulated pulse, that's the case. And also what we call a bed of spikes, where energy is contained within each of these spikes, various amounts. Now these spikes aren't delta functions. They have various amplitudes, and range pulse burst waveforms fall in this category. Now for the knife edge, the ridge type, right here, here's the linear frequency modulated pulse where range and Doppler are coupled. And the knife edge, the ridge, is used to measure one parameter, range, Doppler, or linear combination of range and Doppler, depending upon the orientation of the ridge. There are two examples: a single linear pulsed sine wave, which I'll show you later, or in 2 dimensions, or a single rectangular linear FM pulse, which is right here. And you see here that it's showing you the coupling between your time measurement or range measurement and your Doppler measurement. It says it's ambiguous as to where it is, where how much of the response is due to the Doppler of the target and how much is range, but it's along this curve, the ridge. Now then, to the better spikes used when you measure both range and Doppler with the ambiguities, and they're a burst of end pulses of sine waves. You have that. And then finally, a knife edge. It's also called a thumbtack. It's an example is a pseudo-random noise waveform where you have a spike and the energy that isn't in the spike has got to be somewhere, and it's uniformly spread around a long wave of range and Doppler. And it's really used in radars. Ambiguity functions for 2 simple signal pulses, each with different pulse width, is shown here. And what we've shown are 2-dimensional slices across the ambiguity function, where this region shows you a region of high in the it's like a slice across a mountain. And you see that you have much better in this long pulse width, and here where tau is the pulse width, we're going to have more error, less resolution along the range axis, and better resolution across the Doppler axis. And the converse is true for a short pulse. In a short pulse, we're going to have much better range resolution than this longer pulse, but we're going to have poorer Doppler resolution. So the energy's got to go somewhere. And of course, this will be the region of side lobes. Now here we have the ambiguity function for a single rectangular pulse. And it has a ridge, a clear ridge along the time axis, the range axis, a triangular shape. And it's got, along the frequency axis, it's got a sine x over x shape. Okay? And here is a more mosaicked form of a linear frequency modulated pulse. This book, Gus Rejection wrote a book on ambiguity functions and high resolution radars and waveforms a long time ago, almost 40 years ago. I had a copy of it, I remember. 35 years ago, where he first did the calculations formally, and the book has an awful lot of formalism, but he developed on what was then very new computer technology, these graphs that would take care of the shadowing and the like. Now you can do it with a split second and calling up some MATLAB to make these shapes. You can color them different ways. but it was a boon to understanding the two-dimensional shapes and seeing them in a three-dimensional form. See this three-dimensional system of curves and whatever. And for a long time before people developed the newer software and technology, when you wanted to understand things about certain pulse waveforms, people would just grab Gus Ryachuk's book. And here's the ambiguity function for that linear FM pulse. And the angle of the ridge is determined by the bandwidth over the pulse width. The bandwidth is F2 minus F1. And here are all the different dimensions. You can see this if this angle is twisted over so that this line is along this axis. It becomes that simple pulse as we had before. And here's what the crosscuts would be for a burst of 5 rectangular pulses. And the pulse radars usually use a filter match to one pulse and then integrate the end pulses. And the spikes illustrate the blind speeds and the blind ranges. Okay. And here's the 13-bit Barker code, which almost looks like a bed of spikes. It's a pseudo-random noise code is one which has a very, very long length to the code, and that would flatten down enormously all the different side lobes, and you'd have just this one peak up. But the Barker code, remember, has uniform side lobes of 23 dB, and that's what they look like here. 22.3 dB, I think it is. And lastly on, what I'd like to do is give you a preview of the next lecture, which is going to be about how we apply pulse Doppler waveforms to airborne radar issues which are unique. And here are some platforms which you use pulse Doppler techniques. It'd be the radar in the nose of a fighter. You know, you've got a small area in that nose, so you've got to have a small antenna. And if you want decent beam width, then that's going to constrain you to small wavelengths. And those small wavelengths, that's going to constrain you to a certain place on the ambiguity diagram. And that's going to say, uh-oh, I've got to have these PRFs and these range ambiguities or whatever. And that's going to say a lot about what waveforms you can use. For planes that do airborne early warning radar, they just say, I can't stand putting into the nose of a plane a lot of transmitter. And so what I do is I'm going to put a fair-sized antenna in a radome on top of a plane. And that's what the airborne early warning radar system, the AWACS, Airborne Warning and Control System, that the radar inside this rotating radome is designated the APY1. And for the APS 125 here, which is in the E2C, the E2C is carrier-based, and what it essentially does is can be lifted off of the carrier. You can get up to its maximum altitude and operate this radar, so you can have a radar that can deal with far-away threats to the fleet or a battle group, because this would be far above the line of sight of an aircraft carrier that might have a height above the ocean of 100 feet or so, or 100 and something. This can take you up to many tens of thousands of feet and give you over the line of horizon for the aircraft carrier elements of the fleet and send down information on threat aircraft or missiles or what have you. So you can see that we've got here constraints certainly also of area and here of area. And so there's going to be this whole pulse Doppler issue for airborne radars. And here is the fighter example. If you had a X-band radar, okay, we're at X-band. So we're on this line somewhere. And if you just look in the middle, you'd have an unambiguous range of 10 nautical miles, and a PRF of 8,000 hertz with a blind speed of 270 knots. So clearly, you're going to want to see further than 10 miles. You know, if a plane going Mach 1.5 is facing a plane going Mach 1.5, that doesn't give you much time. You've got to see them well ahead of time to do something about it. So 10 nautical miles as a range is acceptable. And an 8 kilohertz PRF at X-band gives you 270 knots of up to the blind speed. So you're going to be ambiguous in velocity. So here's for an X-band fighter aircraft, you're going to be, just this case, ambiguous in range and velocity, and just how ambiguous, how much you are, where you fall for an X-band radar on that curve down to 40 miles, then your unambiguous velocity would be like 60 miles. That's ridiculous too. So you've got to deal with these issues. And so you're going to deal with the range Doppler ambiguity problem with airborne radars. And now just look quickly at the characteristics, because I'm going to go through them in detail in the lecture, and I don't want to bore you the second time. When you have an airplane that's up in the sky going, we'll call it whatever this is, we'll say Mach 1. The radar measures with its Doppler velocity the relative speed of the aircraft relative to what it sees. So if you're on this aircraft with the radar, the Earth will be Doppler shifted. So a stationary Earth is going to be Doppler shifted, and you see here beams that are different places on the Earth. And so the Doppler frequency of the target is going to depend on the scan direction. And the Doppler velocity of the main beam clutter is going to depend on that scan direction. And the Doppler velocity of the target here is going to depend not only on the scan direction, but also on the aspect angle. Okay? And in addition to that, because the aircraft, is relatively close to the ground and you're looking out at far distances, the side lobes of the antenna will illuminate the ground, and they are shown here as a bump, and here as a little bit bigger bump. And when you're broadside, you're going to get the biggest bump from the side lobe clutter, and then you'll get some more. So the target sometimes will compete with side lobe clutter, or up here where this cruise missile, an example of a target, would be going straight at this aircraft. You'd be having a very high Doppler frequency, and it would be competing just with receiver noise. But tail on, it would be receiving, it would be closer to 0 Doppler, and it would be far smaller Doppler. Now, in summary, pulse Doppler radar techniques can be optimally used, can optimally reject various forms of radar clutter. And the MTD I showed you earlier is an example of a low PRF radar that's near optimum Doppler processing and associated adaptive thresholding. If it were implemented today, it would be implemented with just a bank of transversal filters and not the way it was exactly if you read the literature back in 1969. It'd have nothing compared to the cost of 1,000 ICs all wired together. Just itty bitty. I mean, remember the A to Ds, big boxes, heavy, 30 pounds. You know, they're a chip now. And the ambiguities in range and Doppler can be resolved by transmitting bursts of waveforms at different PRFs. I told you about the Chinese remainder theorem, and we talked a little bit about the ambiguity function as a useful tool to understand the time and frequency properties of the different radar waveforms. And here are a set of problems from Skolnick. They're going to take a little longer than usual because this is a very important part of radar processing. And you should really get these all done if you want to have a good, solid understanding of how radars work that have to deal in a clutter environment. And here are a list of references. And if you want to see how 33 years ago, 34 years ago, how someone would implement the MTD, this is how we did it at the laboratory that many years ago, and it's something you can do in PowerPC. I love it. Technology is great. And more references. I mentioned to you earlier Herman Rowling's treatise. If you can get, I just have one copy left, and I know there's one at the MIT Lincoln Lab Library. If you're at a major radar institution, you probably should have one in your library, or should be able to get a hold of your librarian to get a hold of one. This is the FAA's report on the MTD. And there was a second generation MTD upon which the ASR9 was based. And here's that paper by Hofstadter and DeLong that was in the information theory. And they referenced the paper by Rumler at GE, who were co-inventors. And here's a great paper that's in the Proceedings of the IEEE and Volume 2 and Volume 73, Number 2, that John Taylor et al. From Westinghouse, which is now Northrop Grumman, gave a very good description of the implementation of the ASR9, which the FAA calls the gold standard for air traffic control radars. And lastly, again, my thanks to the late Ed Mewey and to Jim Ward.